Hi, and welcome to a course for Calculus 1 where we investigate some limits at infinity and vertical asymptotes specifically for this video, and then following this we'll look at some horizontal asymptotes. But I really want to dive into some of these problems with you so you can see how a vertical asymptote is linked to the idea of a limit. So let's take a look at what I mean. All right, if we're specifically looking at this question right here, find any vertical asymptotes of the function. What we've studied in the previous video and in your previous courses, hopefully, is that the first place you probably want to start is any point of discontinuity because of that denominator. So let's go ahead and take a look at where is this denominator 0, and we're also going to have to look at the possibility of us having 0 over 0 because that will not turn into be a vertical asymptote. But let's just start by how do I set x cubed minus 2x squared plus x minus 2 and figure out where that denominator is 0. Well, I hope you see factor by grouping. I sure do. So I can take an x squared out of the first two. That leaves me with 1x minus 2. And then out of the second grouping here, I will take out a positive 1. That leaves me with just that x minus 2 as a factor. So I can see that now I have a GCF of x minus 2 in each of those terms. There's only two terms. I've underlined each. Each term has that x minus 2 factor. So x minus 2, and then the leftover is x squared plus 1. Now before I set this equal to 0 and finish solving, I want to do a rewrite here of h of x. All right, so my numerator, I hopefully can recognize that I can factor into the conjugate pair, x plus 2 times the quantity x minus 2. And I've just factored this denominator. X squared plus 1, sorry, that's h of x equals. X squared plus 1 is a sum of squares, which we should hopefully recognize to be prime, so that does not factor anymore, so that's why I stopped there. So this is in fully factored form. Now if you recognize I have a removable factor of x minus 2, that's that removable discontinuity, right? And that removable discontinuity, we did learn that that will turn out to be a whole. So at the value x equals 2, because that's what makes that value 0, I should see that I have a whole. But let's just continue down this path over here of finding vertical asymptotes. We said let's just start by taking that denominator, setting it equal to 0. I factored the denominator, so now by the zero product property, I would say this factor equals 0 or that factor equals 0. So I solved x minus 2 equals 0 to get a positive 2, so I think this will be one of my solutions, but we're going to talk about that in a second. And then if I solve x squared plus 1 equals 0, I should recognize x squared will equal negative 1, and that will not be a real solution. And we're only concerned with the real solutions. Right now I'm trying to find vertical asymptotes on a real Cartesian plane, so I don't need those imaginary solutions. All right, so if you're going back over here, I would think x equals 2 and maybe be done, right? I set my denominator equal to 0. So let's check it numerically. And what I would do to check this numerically is I would substitute in the value that I think is a vertical asymptote into my original function. So if you think you have a vertical asymptote at that x value that you found, a positive 2 here, then that's what we're going to substitute in and check. So h of 2, and again, go back to the very original h function. So go back up. So that would be 4 minus 4 all over 8 minus 8 plus 2 minus 2. So h of 2 is 0 over 0. And if I get 0 over 0, remember when we did limits and studied limits, well, this told us that we had some algebra to do and that it was a removable factor, that I could use my algebra skills, maybe a complex fraction, common denominator work, factor and reduce, something like that. I could do something where I could remove that factor and then substitute in my value. So 0 over 0 was powerful for us with limits, and it still is now. This is telling me that at x equals 2 that I have a hole, not a vertical asymptote. Well, that was my only solution to where my denominator was 0, because remember, x squared plus 1 over here left me with no real solutions. So the only discontinuity that I had in this problem was a removable discontinuity, so it turns out to be a hole. So if I actually answer this question, find any vertical asymptotes, I would say no vertical asymptotes. None. Now, I have shown how I came about that algebraically, sort of in that first column there. I have checked it numerically. I have gone through, again, what does that removable discontinuity or algebra look like when it's written as a fraction? So why was it removable? But what I haven't done is looked at the graph. So let's take a quick second and look at that. All right, so in my y equals, I will type in this function. The numerator was x squared minus 4, so it's important that that all goes in parentheses. And then the denominator was x to the third minus 2x squared plus x minus 2, and again, the entire denominator goes in parentheses. Make sure you are typing in the original function, not the one after you've removed, because you want to check to see, was that in fact a correct factoring and was that removable? You want to see what it looks like from the original function. So if I hit graph, well, this isn't a very large graph, right? Because you're dividing a quadratic by cubics. That probably makes sense to me. That it should be approaching, 0 for horizontal asymptote, which we'll talk about in the next video. But I can't really see at x equals 2. So first of all, I noticed that there does not appear to be any vertical asymptotes right throughout my graph. But my graph appears continuous. It appears that from negative 10 to 10 at least, that I could draw the whole graph without picking up my pencil. That is not the case. If you calculate the first choice as value, so hit enter, calculate a value at x equals 2, you will notice that your y value is blank. Now you do have a limit as x approaches 2, because I can calculate, for example, 1.999, and I could calculate 2.001, so just on the other side of x equals 2, and both y values are approximately the same. But I do have that hole there at x equals 2, so that also verifies I don't see any vertical asymptotes. Okay, now we're only going to do one of these 6 questions, A through F, here in this video, and I hope that you're going to be able to see why. One of these things does not look like the other. Do you know which one? Well, and a lot of people say E, and they're correct, but not necessarily for the right reasons. So why does this one not necessarily resemble the other problems? Look at the limits. Question A is asking as x approaches infinity. B is as x approaches negative infinity. C is x approaches infinity. D is x approaches infinity. F is x approaches negative infinity. Those are all long-term or end behavior type questions. What is the graph doing at the ends of the graph? Those will be linked to our horizontal asymptotes. E is not. E is asking as x approaches pi over 2 from the right. So this is not an end behavior question. This is an intermediate behavior question. This is going to link potentially to a vertical asymptote maybe, or just to another limit, but it's within our function, not necessarily at the ends of our function. So we're going to take a look at this question right here and see how this is linked. So we probably have never seen e to the tangent of x before. And that's the idea of composite functions, right? Instead of it just being e to the x or tangent of x, we can combine them together and now start talking about a little bit more interesting functions. So if you were going to substitute, because remember when you evaluate limits, the first thing that you should be trying every time is just direct substitution. So if I could, I would be putting pi over 2 in for x into the tangent of x part. So let's just try to figure out tangent of x here as x approaches pi over 2. So can I evaluate tangent of pi over 2? If I can, then I don't even really need the side because it's probably the same from the left and from the right if it's the function's value. Not always, but in this case probably would be. We would be along a curve. Well, what does the tangent of x graph look like? So let's quickly draw that. Here's an x-axis, a y-axis. It sort of resembles the shape, if you will, of x cubed, but remember it's trigonometric, so we are cyclic or periodic. Do you remember the period of tangent x? The period was pi, right? So if, trig is very much like your clock, right? You spend an equal amount of time in each quadrant as you go around the unit circle, for example. You're not going to slow down necessarily in one quadrant and speed up in another. The same is true for a clock. Whether you want it to or not, that second hand is moving at a very constant speed. So it's very symmetrical, very cyclical, easy to identify patterns often. So if tangent has a period of pi, one cycle, right, is split up from that y-axis. So then this would be pi over 2 as a vertical asymptote, and this next one would be 3 pi over 2, or one more pi. And if we wanted to, we could say this one over here is negative pi over 2. And of course, the graph goes forever in either directions, but I'm not needing both directions. So now I can see why I cannot evaluate tangent of pi over 2, right? Because tangent of pi over 2 does not exist. Why not? Well, tangent is sine of x over cosine of x. So if I try to evaluate this, I have sine of pi over 2 over cosine pi over 2, and that is 1 over 0. Okay, so getting back to my tangent graph here, that's why I have a direction attached, because also if you look at pi over 2 as a vertical line here, I have two different limits. I have one going up to positive infinity and one coming down here at negative infinity. That is often the case with your vertical asymptotes. You will approach some finite value, but as you approach that finite value, your function or your graph might be approaching positive infinity or negative infinity. So if you're talking about as x approaches 2, so limit of some function as x approaches 2, and you get infinity as an answer, you very well may have, may not, but you may have a vertical asymptote there. More than likely, you do. All right. So let's go back to our problem then. So if I can't evaluate tangent of pi over 2, and I know I go to one of the infinities, now it's where my side becomes important. X is approaching pi over 2 from the right. So from the right, I'm coming down here at negative infinity. So instead of tangent of x, this is going to approach e to the negative infinity. Well, what does a negative exponent do? Do you remember? A negative exponent reciprocates. So this will be 1 over e to the infinity. And 1 over something infinitely large, some people just like to write 1 over big, or 1 over infinity, is infinitely small. So this limit should approach 0. And the interesting part of this whole thing is I never graphed e to the tangent x. You can certainly do that and see if your graph is looking like it's approaching 0, but I just looked at where would I first substitute in the pi over 2. Can I? No. Okay, well let's evaluate tangent of pi over 2 from the right as a limit, and then e to that value. So let's look at the graph just to verify that our answer is correct. All right, so I've gone to my y equals, I've typed in e to the tangent x. It is important to note that unless you want to change your window, you really want to make sure you're calculating in radians, because again, our standard window is going from -10 to 10, which is more than one rotation in terms of radians. One rotation around that unit circle is 2 pi, which is 6.28-ish. But one rotation around in terms of degrees would be 360. So in order to see a complete graph, you would need to go around in your rotation or around your unit circle at least one time to get one cycle of your graph drawn. And as we know from here, we probably want to see more than one cycle because we're looking past that first vertical asymptote, so to speak. So you really want to make sure if you're not changing your window, that you just stay in radian mode. It also keeps everything in terms of pi, which is a little bit easier to deal with. Now, the one thing I will say is since you're dealing with trig and our x-axis here and our vertical asymptotes are all in terms of pi over 2's, you can absolutely change your graphing calculator to display that as well. I don't need to see any negative x values, so I can just start at 0. If you're like me and you really like to see all of the axes, you can start just a little bit on the other side of that x min or x max, but if it doesn't bother you, you can start at 0 for this one. Maybe I'll go to 2 pi, or maybe I'll go to 5 pi over 2, doesn't matter truly. Just go to something. Again, you can just type in the pi, it'll calculate it. But I like to calculate for this one in terms of pi over 2, so my tick marks will make sense. Okay? Now, why is this graph only above the x-axis, or is it? One quick thing to note is that if your graph comes down too sharp and it appears like it's a vertical line, your calculator will stop drawing it. So you need to be able to look at this and identify, is this going into the negatives or is this actually stopping? Well, you are raising e to some power. E is a natural number that will be studied that's a little bit more than 2. So it's a positive value that you're raising to some power. You will always have then a positive output. Okay, so that kind of makes sense. And we're trying to approach pi over 2 from the right. So again, if I could calculate a value at pi over 2, I probably would like to do that. That would be the most beneficial, but it gives me an blank, and in my table of values it will give me an error. But it does tell me the decimal, 1.5707, etc. So I could, if I wanted to, go to my table of values here. I'm going to get out the old ones. And I could say 1.571. That's just to the right-hand side of that value. And it does tell me that it's 0 or very, very close to 0. If you do something like 1.58, it's kind of estimating that for you. It's 6.5 times 10 to the negative 48, so you'd move that decimal point over 48 places to the left. That's resembling 0. So I hope this helps get you started with vertical asymptotes. They're links to limits. Thanks for watching.